In this video, I will attempt to give you a broad overview of the different types of statistical tests that exist, as well as some perhaps helpful tips and hints on how to choose the proper statistical test when you run into a problem. What I've done in this graphic is to try to divide all the various statistical tests into broad categories. These are some of the more common or widely known tests, and you can see based on the colored rectangles here that they can fall into different categories. Commonly we're looking for differences in groups, and that might be men versus women or customers versus non-customers, what have you. And so the tests you see here, ANOVA, t-test, z-test, are all ways that we can test that. Z-tests tend to be most commonly used with proportional or discrete data, t-tests for continuous data, and analysis of variance for a combination of both discrete data and continuous data when we have more than one sample. An analysis of variance, ANOVA, is a bivariate test where we have two variables. Another type or category of tests are what I call degree of association. That is, that there is some kind of connection, however it's not as strong as a degree of relationship. Here we'll be using either a frequency table or a homogeneity table, which is commonly called a two-way table. And these two techniques look at discrete data, categories, if you will. Correlation is for continuous data, where we're trying to see how one variable may mathematically relate to another. The relationship data tends to be more mathematically oriented, and all of these require calculations for the most part. Regression is by far the most common, and we can use Excel to calculate that. However, multidimensional scaling and cluster analysis both require special software programs. If we want to see if a particular variable can be predicted into different categories, then logistic regression or discriminant analysis become the tools of choice. And both of those are what we call multivariate type tests. In other words, there are many variables. Last but not least, and probably the most complex, are what we call tests for structures, trying to see the underlying configuration, mathematically speaking, of variables. And so whether we have exploratory factor analysis or confirmatory factor analysis, path analysis, all of these are far more complex. Now, how do we go about choosing a particular test? What I've tried to do here is to create a flowchart that would help to determine which test would be appropriate for the problem you're facing. And you'll notice that the diamonds here, which are all decision type symbols in flowcharting, you'll notice that the main question is, actually there are three main questions that get you to the appropriate test. The first one is, how many variables are we dealing with? Are we dealing with a single variable, something is being measured, or do we have more than one variable? Now, because we're looking at inferential data and we're looking at it as sort of an introductory perspective, then I'm only going to deal with some of the simpler bivariate analysis. So let's assume that we have but one variable. The next question asks is, how many samples do we have? If we have only one sample, one variable, one sample, then we're going to fall into this block, and you'll notice that the tests here in sort of a turquoise color tend to be either z-tests or t-tests. If we have if we have two samples, then we're going to fall into this group here, which tend to be sort of the tan color, and you'll notice that we start seeing two sample tests. T-tests are by far the most common, although you can have a z-test. And if it's more than 2, then commonly we'll be using a chi-square. The last question to be answered is, what type of data are we dealing with? Is it a category or a countable object type variable? Then it will fall into what we call discrete. Discrete data are measurements that can only exist in whole numbers, if you will. Countable objects is the way I like to refer to it. So the number of cars in the parking lot, the number of students in a classroom, the number of customers versus non-customers, all of those are countable objects. The variable itself, that label, can't take on an infinite number of values. In other words, I can't have 2.3 customers waiting in line to be served. I either have 2 or I have 3. So when I have one variable, one sample, discrete data, I'm running a z-test. If it's a variable that has kind of an infinite number, can take an infinite number of values, for example, weight, we can have partial pounds or ounces or whatever. We can have 2.3. In other words, we don't measure in only whole pounds. Therefore, it's continuous data. Then we come down to one last check, and that is, do we know something about the population variance? If we do, then we'll run a z-test. Commonly, we don't know that in most circumstances. And so when we don't know the population variances, not the sample, but the population variance, then we're running a t-test. Now, what happens when we have more than one sample? Okay, let's take the situation where we have 2 samples. What type of data? If it's discrete data, then we'll be running a z-test, and this would be like the proportion or the percentage of people who are in favor of something versus a percentage of people who are not. We see a lot of z-testing scenarios when we get into an election year, for example. Those who would vote for a particular candidate versus those who would not. We don't have a partial voter, we have a full voter. So when it's a discrete data element and we have 2 samples, then we're running z-tests. What happens if we have one variable, say it's preference, we have 2 samples, preference of men versus preference of women, then if preference is a continuous variable, in other words, we can have on a scale, we can have a 2.4 number, then the next question we have to answer is, what is the relationship between those 2 samples? If it's dependent, then we run what's known as a matched pair t-test. If it's independent, then we have to check one more situation, and that is something about what's the variance like. And we do that through an f-test. An f-test is nothing more than a ratio of variances and allows us to determine whether they are similar or not. And if the variances are considered to be equal, then we run a t-test with equal variances. And if they're not, we run a t-test with unequal variances. Now, these t-tests that are listed here for 2 sample continuous variable tests, all of these are performed by Excel. So therefore, you must determine which situation it is so that you'll be able to select the proper test. The univariate one variable data type tests, Excel will not run. And if you remember, I've created a separate univariate spreadsheet that has the processes built in. Now, the question you may have, and I haven't answered, is how do I know if I have a dependent or an independent? Well, this graphic should help make that clear. If the 2 samples come from different populations, in other words, sample A comes from population A, sample B comes from population B, they're considered to be independent. Now sample A and B may actually be in a single electronic data file, but the actual elements themselves come from separate populations, as opposed to what we call dependent samples, where we have two measures from the same element in the same population. So commonly what we see this test or this situation arise is when we have like a before and an after. We take a measure of elements of the population. Something might happen in between, a procedure, a test, a seminar, a program, what have you. Or even in medical testing, drug testing, we might have the medication provided, and then we take a second measure of the same elements. That's a dependent, often called matched pair. So hopefully this will give you a little better sense of how to determine not only what samples, how many samples I have and what the relationship is, but also which statistical test I need to run.